Hello everyone. Welcome back. We're talking about collision resolution using open addressing, and we saw the example with linear probing. So using the linear probing, let's see how we are going to find an item in the linear probing using the linear probing. Okay. So let's say we are looking for item 9. Okay. The hash value gives us the hash value gives 9 for the value 9. Okay, so first we are going to look at the cell 9. 9 is not there, then we are going to look for the next cell. Okay, 9 is still not there, then the next cell, 9 is still not there, then the next cell. Okay, and that's how actually we are going to keep looking until we find an empty cell. Now let's see, we are looking for item let's see we're looking for item 28. Okay, say for 28 the mod value 28 mod 10 is 8. Okay, that means we are going to look for the item at the cell 8. All right, so 28 is not there, then we are going to look at the next cell. 28 it's still not there, then we are going to look for the next cell. Not there, not there, not there, and we found an empty cell, but still we didn't find 28. Okay, that means 28 is not in the hash table. Okay, so when we are going to look for an item, we are going to start from the cell that hash value gives us the value. Okay, if we didn't find the item in the hash value, in the index of hash value, so we start looking for item from the hash value index. But if we don't find the item, then we keep look at the next available cell. Okay, and we are going to keep looking until we find an empty cell. If we find an empty cell but still didn't find the value that we are looking for, that means this value is not in our hash table. Okay, now let's see, if we are looking for 58, how many probe we are going to need. So if we are looking for 58, 58 is going to need us, we are going to start from 8. Okay, then 9, then 0, then 1. Okay, that means 1 2 3 4. All right, if we are looking for uh, 9, that is going to need us, we are going to start from 9. 1 2 3 4, that will also take 4 probe. Okay, so looking for 9 is going to take 4 probe, looking for 58 is going to take for 4 probe. So you can see that here also the runtime, I mean the runtime to search foreign items for successful or unsuccessful search is not actually order of 1, it will be more than order of 1. Okay, now let's do some we're going to do some analysis. What is going to be the runtime for successful and unsuccessful search. But although this is going to be more than 1, but still we'll see that the runtime will be still close to constant time. Okay, it will be at least less than it will also depend on actually the load balance. All right, and it will be less than the size of the table. Okay, obviously. So deleting in hash table is known as lazy deletion. So what is lazy deletion? Lazy deletion means actually we are not going to entirely physically delete the item from the hash table. Instead of that, what actually we are going to do in the hash table, so we are going to mark the cell like deleted. Okay, we are going to, instead of entirely delete the item from the cell, we are going to mark the cell as deleted. So when we are going to insert a new value, then the insert function will find this cell empty. Okay, so that they can insert a new value in that cell. Okay, but the purpose of lazy deletion means actually we are not going to entirely delete the value from the cell. Instead of that, we are going to mark the cell as deleted. Okay, So the main problem of linear probing is that it creates actually a clustering problem. All right. So if the table is big enough, most of the time actually, if the table is big enough, we will always find a free cell. All right. But the problem is that if we start inserting item in the free cell, all right, it creates actually an clustering. So clustering means actually you can see that. So we here in this example we had actually collision for these two value 89, for this three value 89, 49, 9. Okay. So the table was comparatively empty, so that's why when we didn't find an cell for 49, actually we inserted in the next cell. Then for 58 we insert in the next cell, then for 9 we insert in the next cell. So it actually creates like a primary clustering. Okay. So what happens if there is a lot of clustering? If there is a lot of clustering, the number of probing is high. Okay, because the algorithm to find an item means actually we are going to keep looking for the item until we find an empty cell. So if there is actually like a large cluster, that means actually we have to look for every item in the cluster. Then when we find an empty cell, we'll know that the item is not found. Okay, but before that we have to, in worst case, we have to look for every item in this cluster. Okay, so here the linear probing, the problem is that it will form like a cluster. Okay, so any key that will hashes into the cluster will require actually several attempts to resolve the collision. So inserting an item or finding an item, you have to actually go over all of the values in the cluster. Okay, for insertion also, if there is a large cluster, you have to actually find an empty cell by actually traversing all the items in the cluster, and then you have to look for the empty cell. Okay, so the average number of cells that are examined in the insertion after linear probing is roughly this value here. This one is known as load balance. Okay, all right. So here this proof is beyond the scope of this class, so we are not going to go with the proof of this equation. Okay, so but roughly the insertion, roughly the number of probing for insertion is this equation. Now for a half full of table we obtain actually 2.5 as average number of cells examined during an insertion. So if the table is almost half full, in that case the for insertion it is going to take average 2.5 number of cells. Okay, so primary clustering is a problem at high load factor. So for a half empty table, the effect is not actually disastrous, but if there is a large primary clustering, in that case actually, if there is a large primary clustering, you have to actually look for every values in your cluster. Okay, so an unsuccessful search is same as insertion. Okay, so because you can see that an successful search means you have to actually look for every item in the cluster. For insertion also you have to look for every item in the cluster. I mean you have to scan every item in the cluster, then you will find an empty cell. Okay, and for unsuccessful search means it's actually same, means you have to look for every item in the cluster, then when you find an empty cell it means that the item is not in the hash table. Okay, and now the cost of successful search x is equal to the cost of inserting x at the time when the x was inserted. So if the load factor is 0.5, the average cost of insertion is 2.5. Load factor is 0.5 means actually the table is half full. Okay, in that case the cost of insertion is 2.5. So you can see that actually, I mean, even though the cost is greater than 1, still actually the cost in the hash table for successful or unsuccessful search is actually a constant time searching mechanism. Okay, Alright, so the average cost of a successful search is an average of the insertion cost overall the smaller load factor. Alright, so the roughly the searching takes actually the cost of like this. As we said, we are not going to actually go with proofing this mechanism, but the equation looks like this. Okay, and here also you can see that actually the size of the table doesn't matter, rather than the load factor is a important factor for open addressing also. So here is an example. We are going to see the average probing for a hash table. Okay, so let's see here we have the table size. You can see that the table size is 11. Okay, so our hash function is x mod 11. All right, so let's see the successful search. Say we are looking for uh, the value 20. Okay, we are looking for the value 20. So the hash value hash of 20 is 9. Okay, so we are going to try to find the item at the index 9 20. So we need one probing. So one probing for item 20. So we're looking for item 30. 30 mod 11 is 8. Okay, so 30 mod 11 is 8. So let's look the item 30 in the index 8. We found the item, so number of probing is 1. Okay, and here for 2 also number of probing is 1. So for 13 our hash value is 2. Let's see, look for the item. Let's see, look for the item 13 in the index 2. Okay, so it is not there, then we are going to look 13 in the next cell. Okay, then we found the item 13 here. So number of probing for item 13 is 2. So same as number of 25, it will be 2. For item 24, let's see to what will be 24. So hash value of 24, it will be 24 mod 11. So it will be 2. Okay, so we are going to look for 24 in the 2. 24 is not there, then we are going to look for the next one, not there, then the next cell, not there, then we are going to look for in the 5. Here we found the item. Okay, so if we don't find the item, we are going to look for the next cell. We will see that here this is an empty cell, that means 24 is not there, but we found the item 24 in the cell 5. So how many probe we need? 4. 1 2 3 4. So for 24 we needed 4 probe. Okay, and that's how for 10 we need 1. For 9 we need 3. So the average probe we need actually sum of all of them divided by 8. 8 is the number of item that we used for successful search. So it was 15 divided by 8. Okay, so for this hash table, this is our average probe for successful search, and that's how we can find unsuccessful average probe for unsuccessful search. So let's look for an item. Let's see, we are looking for item 9. Okay, so item 9 mod 11. So 9 mod 11 is 9. We are going to look for the item at the 9. So 9 is not there. Okay, so here actually in this hash table we have already 9, so we're not going to use this example. All right, so we're not going to use this example. So let's try to find the item 8. Okay, so 8 mod 11 is 8. So we're going to start looking for index 8. So 8 is not there, then we're going to look at the next cell. 8 is not there, then next cell 8 is not there, next cell 8 is not there, then we find an empty cell. Okay, so if we find an empty cell but still we didn't find the value, that means 8 is not in the hash table. Okay, so how many probe actually we need? 1 2 3 4 and 5. Okay, for 8 we needed 5 probe. All right, so for 3 we are going to need, actually we are going to start looking from the index 3. 3 is not there, 3 is not there, 3 is not there. Then at the index 6 we find an empty cell. That means we will know that 3 is not in the hash table. So for 3 we needed 1 2 3 and 4 probe. Okay, so this is the that's how we can find actually how many probe we are going to need for an unsuccessful search. Okay, and we can find actually for a couple of value, like for a couple of value, that what is the average number of unsuccessful search we are going to need. Okay, now the main problem in the linear probing is the clustering. Okay, so if the cluster gets actually larger, in that case actually the number of probe to find an item to number of probe is going to get high. So in the quadratic probing, it's actually the same idea we are going to use. The open addressing means actually we are going to resolve the collision using the same hash table. But here we are going to use the function f of I equals to I square. Alright, so that means now our hash function will be h of x plus f of I mod table size. Alright, but for quadratic probing, f of I we are going to use I square. Alright, so for I square, the index we are going to look for, the I value will start from 1 2 3, alright, until table size -1. So here actually the I square, because we are using the I square, so the next table we are going to look for 1 4 9, that's how. Okay, so instead of looking for the next cell, we are going to look for the quadratic way, like we are going to look for the next cell with 1, then the item, then the cell 4, then the cell 9, like that. So let's see an example. So let's insert 89. So 89 mod 9, 89 mod 10 is 9. So the cell 9 is empty, so we are inserting 89 here. So then insert 18. Okay, so the hash value is 8 cell is empty, so we are going to insert 18 here. Okay, so then let's insert 49. So 49 mod 10 is 9, so the cell 9 is already there is a value, so collision, that means we have to find another cell. Okay, so for quadratic probing, we are going to use hash of x, which is 9, plus f of I, which is I square, and here we are going to start I with 1 2 3, like that. Okay, and so on. So we are not going to start from 0, because we are using the square of that. 0 square is same as 0. Okay, so we are going to start from 1. Okay, so I equals to 1, so let's start from 1. So 9 plus 1 square mod 10, which will give us 10 plus mod 10, 0. Okay, so we'll see that 0, the cell 0 is empty, we're going to insert 49 here. Okay, then let's insert 58. So for 58, the hash value is 8. Alright, means collision. Okay, so means collision means we have to resolve the collision, so we're going to use h of x, which is 8, plus f of I. We're going to start from 1 square. Okay, mod 10, which is 8 plus 1 mod 10, 9. So 9 is still collision, so we're going to try, then the next value we're going to try with 2, but 2 square mod 10, so which is 8 plus 4 mod 10, so 12 mod 10, which will be 2. Okay, so this index. Okay, so index 2 is empty, so we are going to insert 58 here. All right, then let's insert 9 again. So 9, the cell 9 is empty, sorry, the cell 9 is, there is a value, so collision. So how we are going to resolve that? 9, so h of x, which is 9, plus 1 square mod 10, which is 9. All right, collision, then 9 plus 2 square mod 10, which will be 9 plus 4 mod 10, okay, which will give us the 3. 9 plus 4 means 13 mod 10, 3. So the cell 3 will find it empty, and we are going to insert 9 here. Okay, so let's try to insert 28. Okay, so if we try to insert 28, so 28 mod 10 is 8, so which is actually a collision. So how we are going to resolve that? So 28 mod, we are going to try with 28, so let's use eraser. So 28 plus 1 square mod 10, which will be I'm sorry, the hash value is 8 actually for 28. So 8 plus 1 square mod 10, which will give us 9, collision. So then we are going to try with 2 square. So 8 plus 4, 12 mod 10, which will give us 2. Okay, so 2, the index 2 is a collision. Then we are going to try with 8 plus 3 square. Okay, so 8 plus 3 square means 8 plus 3 square 9. So 8 plus 9 means 17 mod 10. Okay, 17 mod 10, which will give us 7. So 7 will find this cell empty, and we are going to insert 28 here. Okay, so here you can see that we are not actually just going to insert the item at the next available slot, rather than it is going to be slightly scattered. Okay, it will be slightly scattered, so that it will not create a clustering. Okay, it will not create a clustering problem. So so here the problem is that we may not be sure that we will probe all the locations in the table. So in the linear probing, we know that we are going to use all the locations from the table, but here in the quadratic probing, the problem is that we may not be sure that we will probe all locations in the table. Okay, so if the hash table size is not prime, this problem can be also a much severe. So the quadratic probing, actually it has not been the thing is that the quadratic probing has not yet been mathematically analyzed. Okay, so it eliminates the primary clustering problem, but elements that hash to the same location will probe the actually same alternative cell. All right, so it known as actually a secondary clustering. So for the secondary clustering, the most popular technique is double hashing. Okay, so in this here we are not going to actually talk about in detail double hashing, but there is another technique known as rehashing. So if the load factor gets too high, all right, if the load factor gets too high, in that case what actually we can do, we can actually dynamically we can expand the size of the table. Okay, we can expand the size of the table, means if our table size is now 10, we are going to expand the size of the table, so probably we can actually double the size of the table. So instead of 10, we can make it 20. So if we expand the size of the table, that means actually we have to do the rehashing. All right, we have to assign each of the number again in the hash table. okay, because we know that the hash function depends on the size of the table, right? So if we expand the size of the table, we have to actually assign each of the value in the, we have to reassign each of the value in the hash table. So the whole technique known as rehashing. Okay, all right, so with this discussion we are going to actually end our discussion about hash table. Okay, so summary is that hash table can be implemented, hash table can be used to implement the insert and find operation in constant average time. So we saw that the for different implementation, the average time could be higher than 1, but still we expect that the average time for searching an item and to insert an item should be constant. Okay, so the search time depends on the load factor, not the number of items in the table. So it's important to have a prime table size. Okay, we actually saw the example with table size 10, but actually real implementation in real implementation the prime number is used as a table size. Okay, and a correct choice of load factor is very important. For separate chaining, the expected load factor is close to 1, and for open addressing the load factor should not exceed 0.5. So if the load factor exceed 0.5, in that case actually we have to use the rehashing. Okay, so rehashing means we have to grow the size of the table. All right, so this is the main idea of the data structure hashing. So here as summary we are going to talk about the summary. That means we talked about the hash table, what is known as hash table, how we do the hashing. Okay, and the hashing could hashing gives us the insertion and finding an item in the constant average time. Okay, but for hashing we have to know about the collision resolution. Okay, and we saw a couple of ideas how to resolve the collision. Okay, and here we saw two ideas especially. One is separate chaining and another is open addressing. And in open addressing we saw the idea of linear probing and quadratic probing, and for each of the collision resolution technique we saw the pros and cons of each technique. All right, so we'll see you in the class.